I didn't see you there. You see, I was just reading here about how Dr. Samuel Beale figured out how plants and algae synthesize amino-levulinic acid, the common precursor for heme, chlorophyll, and violence.
I knew it! I thought we agreed we weren't going to do this intro. This is supposed to be a serious video, James.
You obtuse simpleton. What do you not understand about my artistic vision?
Let me show you what I think about your artistic vision.
Here we go!
You're going to be in for some pain.
You're on.
Alright, come on, everyone! Hey, come on!
Go for the knees! Give him the chair! Give him the butt!
Oh, is this thing on?
What you got there, Caleb?
A cat. The
I
show.
think I'm getting a minor nicotine.
Whatever.
So just do it! Make your dreams come true!
Our story begins in Providence, Rhode Island, where Dr. Beale is working at Brown University. He asks himself,
You know, I wonder how plants actually create porphyrin rings. Now that would be a cool thing to know.
So after this profound question, he set off to find an answer.
he decided to start by looking at different photosynthetic organisms and made sure that the research was done properly. He studied day and night for years, searching for an answer. He slowly started to learn that organisms use different pathways. Some organisms use glycine to form ALA. This was known as the Beale Pathway. Others used glutamate, but it was not understood how glutamate was used.
I must understand how these magnificent creatures use glutamate to form ALA.
And so he set off yet again to slave over his equipment to find the answer. He started with expressed plastid DNA and noticed that ALA wouldn't be formed if an RNase was added to the solution.
Wow, this must mean that there's an RNA molecule affecting its production.
Through further testing, he discovered that tRNA glutamate was necessary for the reduction of glutamate and the production of ALA. Extracting chloroplasts from barley plants, he discovered that glutamyl tRNA synthetase was found in chloroplasts and required ATP to function as a ligase. With further tests, he found that if glutamyl tRNA synthetase wasn't present, then tRNA glutamate would be used but not glutamate. This showed that the formation of tRNA glutamate was necessary for the reaction to proceed.
Wowie! This must mean that glutamate, ATP, tRNA synthetase, and magnesium are necessary to produce ALA.
Ha! One down for the Beale man. He then searched as to how tRNA glutamate is changed into ALA.
You know, if I'm able to gather all the enzymes that work in this reaction, I could separate them from each other and see how they work by themselves.
Pleased with his method to find the answer, he then separated the enzymes from one another. He wanted to see if there was a reductase present, and sure enough, there was, and found that NADH or NADPH would be used, depending upon the species.
Wow, it seems some species prefer NADH over NADPH, and vice versa. I wonder then how the product of this reduction changes into ALA.
He then knew that tRNA glutamate would be reduced by glutamyl tRNA reductase. And and it would use NADH or NADPH, depending upon the species. It was also discovered that tRNA would act as the activator molecule for glutamate. It was necessary for it to be changed into glutamate 1-semialdehyde. Glutamate 1-semialdehyde is then changed by glutamate 1-semialdehyde 2,1 aminomutase. This enzyme transaminates GSA into ALA.
Gee willikers, I finally discovered how these magnificent creatures create ALA. Hey guys, I finally figured out how the plants synthesize ALA.
You?
And so ends our tale of Dr. Beale's journey to find the pathway for aminolevulinic acid. However, this is not the end of our story. I will now turn you over to Caleb, and he will tell us why this finding is so significant.
I thought we agreed I wasn't supposed to be in the video.
Okay, what do you guys not get about my artistic vision?
Shalom, I'm Rabbi Caleb. I'm here to continue explaining how researchers later discovered that the Beale pathway was utilized by other photosynthetic organisms, microorganisms, and plastids. For those who are unaware, chloroplasts within eukaryotic plants are considered plastids. Plastids use their own DNA, not the DNA of the plants, to code for the enzymes necessary for the reaction to proceed. The reaction is primarily inhibited at the aminotransferase by PLP antagonists. The entire pathway is inhibited by heme, but it is not clear as to which enzyme that it affects. The strongest control mechanism for this reaction is the presence of light. When these photosynthetic organisms are exposed to light, the reactions occur at a higher rate compared to those of the reactions in the dark. This makes sense due to plants using sunlight for anabolic processes. Aminolevulinic acid will go toward the production of the porphyrin ring for chlorophyll and vitamins, like vitamin B12 in photosynthetic organisms. In non-photosynthetic organisms, ALA will go towards the important heme group, which is found in both hemoglobin and myoglobin for blood and is also present in the membrane-bound protein, cytochrome C, in the electron transport chain. Interestingly enough, anaerobic archaea use ALA to create cofactor F430, which produces methane.
Rabbi, does this use the Beale pathway?
Yes.
Rabbi, does this use the Beale pathway?
No. It uses the Schimmin pathway.
Rabbi, do these use the Beale pathway?
No.
Wasn't that just a truly beautiful story? Come back next time and we can learn about even more beautiful stories together.
Death to Caesar is an artistic vision.
No!